We've learned several ways that we can calculate or estimate energy changes for chemical reactions. And another way is to use the bond energies. So bond energy is defined as the energy needed to break a mole of that bond in the gas phase. Because the energy to break one bond is just a teeny tiny, minuscule amount. So as with many things, we're looking at a mole of bonds. Bond energies are always positive, meaning you always have to put energy into the molecule to break the bonds. If you have to put more energy in, that means the bond is stronger. It takes more energy to break the bond. We could write a chemical equation showing the bond energy for a hydrogen-chlorine bond. Here we have HCl in the gas state, and now we have a hydrogen atom and a chlorine atom. The only thing that's different here is there was a covalent bond here, and now there's no bond. The energy change for that reaction is 431 kilojoules. That's the energy needed to break that particular bond, 1 mole of that bond. Compounds that have stronger bonds tend to be more stable. That kind of makes sense, right? If you've got some sort of a creation that's glued together very securely, it's not going to fall apart very easily. So strong bonds, those compounds are more stable and they are less reactive. Bond energies are going to be different depending on what molecule that particular bond is in. So we usually look at an average bond energy. If we look at a carbon-hydrogen bond, here we have 4 different compounds. We have methane, trifluoromethane, tribromomethane, and trichloromethane. We're still looking at this carbon-hydrogen bond, but to break a mole of that bond in methane is 438 kilojoules. It's 446 if there's fluorines in there, 402 for bromine, 401 for chlorine. Instead of being so specific and looking at exactly what the bond energy is, we're just going to use average bond energies because this is an estimate after all. So looking at those, they take an average and say, well, it's a 414. Now, a double bond is stronger than a single bond, so it has a higher bond energy, and triple bonds have the highest bond energies. Here's a table from your textbook showing different bond energies. So here we've got, let's look at these, nitrogen, single bond, double bond, and triple bond. 163, 418, 946. So the triple bond is much stronger. One thing I'd like to point out in here when we're looking at, where'd it go? There it is. See the asterisk? A carbon-oxygen double bond. The average bond energy is 736 kilojoules per mole, except it's 799 for CO2. So be aware of that. That's going to come in occasionally. So how do we use bond energies to estimate enthalpy changes? Well, breaking bonds is endothermic, putting energy in. So that's a positive number. Forming bonds has to be negative then. You can't just create energy by making and breaking bonds. What you put in comes out, right? Conservation of energy. So bonds forming is an exothermic process, a negative bond energy. So what we're going to do to estimate enthalpy for a reaction is we're going to look at the total of bonds broken and bonds formed and the energy changes for those. So the heat of reaction is the sum of all the bond energies that are broken plus the negative of the bond energies that are formed. Okay, so this is a lot like a Born-Haber cycle. It's utilizing Hess's law, the state function of enthalpy. So we can estimate the enthalpy of this chemical reaction where methane is reacting with chlorine to form chloromethane and hydrogen chloride. We want to know the change in energy for that. We can imagine a path And even though that path doesn't actually occur, if we know the energy changes for the path, that will give us a pretty good estimate of this reaction, because it's a state function. How you get there doesn't matter, just that you start and end in the same place. So what we're going to do is we're going to look at, well, what bonds have to break in order for this reaction to occur? Well, this chlorine-chlorine bond has to break. That requires that we put energy in. We have to break one of these carbon-hydrogen bonds. That requires us to put energy in. So we put energy into this. It's like an investment. You're sinking money into this project. Now we've separated a hydrogen atom off, and we've separated these two chlorine atoms. Now they're able to react. So one of the chlorines can react with the hydrogen, forming a bond. When a bond forms, energy is released. The other chlorine can bond to this carbon atom, and again, energy is released. So here we have going down, energy is being released. If this energy being released is larger in magnitude than the energy needed to break the bonds, we'll have an exothermic reaction. Any questions? In this example, we're looking at just the bonds that need to be broken and just the bonds that need to be formed. So we're not breaking all of these bonds because we looked at the product and we saw, well, these carbon hydrogens all stayed intact. So this is looking at just the specific things that are happening. Let's do an example. Oh, let's talk about this first. We say that energy is stored in chemical bonds. That's kind of misleading. So when you break a chemical bond, that requires that you put energy into it. Energy is released when bonds are formed. And so an energy-rich compound will have weak bonds, and it will undergo reactions in which strong bonds are made. When strong bonds are formed, more energy is released. So it's the forming of chemical bonds that releases energy, not the breaking of them. Any questions about that? I can repeat that, yes. We talk about energy being stored in the chemical bond, which makes us think that, well, if you have a strong bond, there's a lot of energy in there. And that's actually kind of backwards, because the energy comes when the bond is formed. The bond releases energy when it forms. To break a bond, you have to put energy in. So an energy-rich compound like octane, which is a component of gasoline, that burns, it combusts, and gives off a lot of energy. Where's the energy coming from? The energy is coming because weak bonds are being broken, which takes very little energy to break, and strong bonds are being formed, releasing a tremendous amount of energy. Does that help? Okay, now we'll do an example. So potential future fuel is methanol. Write a balanced equation for the combustion of gaseous methanol and use bond energies to calculate the enthalpy of combustion of methanol in kilojoules per mole. So the first thing we need to do is write a balanced equation for the combustion of methanol. We're given the formula for methanol, CH3OH. And what's the other reactant? Oxygen, O2. And what are the products going to be? CO2 and water. Because when hydrocarbons burn, that's what they form. So we need to balance this equation. So there's one carbon on each side, so that's fine. Over here I have 3 hydrogens and 1 hydrogen, a total of 4 hydrogens. And over here I only have 2. So I can fix that by putting a 2 in front of water. Now I've got 2 and 2. I've got 4 oxygens over here, and I have 2 plus 1, 3 oxygens over there. So that gets a little awkward. How can I make How can I make that into 4? What can I do? I could use a fraction, but most students don't like that. I've got an odd thing on one side and an even thing on the other side. Let's try doubling the coefficients on everything that we've looked at. We'll leave oxygen alone, and we'll double the coefficients for the others. So looking at 2 moles of methanol, and 2 moles of carbon, and making this a 4. Let's double check that we didn't mess up the carbons and the hydrogens. I have 2 carbons now and 2 carbons. Over here, I have 2 of these molecules, each has 4 hydrogens, so that's 8 hydrogens. And over here, I have 4 water molecules, each with 2 hydrogens, so that's 8 hydrogens. So carbon and hydrogen are still fine. Now what we've got 4 oxygens in the CO2 and 4 oxygens in the water, 8 oxygens. And I've got 2 oxygens in the methanol plus, question mark, what do I need there to equal 8? I need that to be 6. To get 6 oxygens from this, I need 3 O2s. So that was the first step, balanced chemical equation. We could look at this and figure out what bonds remain intact. Maybe there aren't any, but maybe there are. In the previous example, the carbon-hydrogen bonds didn't get broken. I don't think that's a good way to approach these problems because it requires an awful lot of thinking. I think it's easier to imagine we're going to break all the bonds in the reactants and we're going to form all the bonds in the products. I think that's a simpler approach. So like if we were building with Legos and we're starting with these structures, instead of just taking apart what we needed, we're going to take them completely apart and then we're going to build them from the loose blocks. Okay? So that's what we're doing. We need to look at the Lewis structure so that we know what bonds are present. Because O2, unless you look at the Lewis structure, you might not remember that it's got a double bond. It's not a single bond. So we need Lewis structures for these things. So I'm going to do this kind of quickly because it's not the point of this. So that's the Lewis structure for methanol. And for oxygen, that has a double bond. And then over here, when we're looking at CO2, carbon in the middle, double bonded to oxygen on each side. Come on. And for water, oxygen in the middle, hydrogen on each side with single bonds, lone pairs on the oxygens. So I'm going to draw a line down the middle here. I didn't really mean to do it with the fat one, but that's actually kind of nice. So what I need to do here is figure out what kind of bonds are being broken and how many moles of each bond are being broken. So in this molecule, I have carbon-hydrogen single bonds. I have a carbon-oxygen single bond. I have an oxygen-hydrogen single bond. And that covers all of the bonds in there. And then in an O2 molecule, I have an oxygen-oxygen double bond. Everybody okay with that? We have to consider how many, because if you break twice as many bonds, it's going to take twice as much energy. So I'm looking at 2 moles of methanol. So in 2 moles of methanol, how many moles of OH bonds are there? 2, right? There's 1 mole in each of these. There's one of those bonds in a molecule. So in 2 moles of that molecule, there'd be 2 moles. So I've got 2 moles of those kinds of bonds. How about the carbon-oxygen bond? 2 moles. And how about that carbon-hydrogen bond? In one of these molecules, how many carbon-hydrogen bonds are there? 3. If I have 2 moles, I'm going to have 6 moles of bonds. Okay? So 6 moles of that. Here in 1 oxygen molecule, I have 1 double bond. In 3 moles of oxygen, I have 3 moles of bonds. Any questions about what I'm doing there? If this was a weird tricycle and these hydrogens were wheels, I would have 3 wheels, right, on 1 tricycle. If I had a dozen tricycles, I'd have 3 dozen wheels. If I had 2 dozen tricycles, how many wheels would I have? 6 dozen, right? Okay. Let's go look at the other side. So, what kind of bonds do I have in my products? Name one. I have a double bond between what 2 elements? Carbon and oxygen. So I have a carbon-oxygen double bond. And there's actually only 2 types of bonds on this side. What's the other one? A single bond between oxygen and hydrogen. Because this bond, carbon-oxygen double bond, this bond, carbon-oxygen double bond, they're the same. And in the water, I have 2 oxygen-hydrogen single bonds. So let's think about the CO2. I'm going to write this out because just talking about it doesn't seem to be working very well. So how many of those double bonds are in 1 molecule of CO2? 2, right? I have, I don't know what that was, 2 bonds per 1 molecule. If I have 2 bonds in 1 molecule, how many bonds do I have in 1 mole of molecules? Not 4. Okay, let's do this. So if I multiply this by Avogadro's number, blah, blah, blah.
You have 2 bonds in 1 molecule and you have
1 mole per that many molecules. This is not going well. So 2 bonds per 1 molecule. What if I had 2 moles of bonds? That would be in how many molecules? 1 mole of molecules? Two bonds per 1 molecule. You okay with that? So if I put mole on top and mole on the bottom, the ratio is still the same, right? You okay with that? 2 moles of bond per 1 mole of molecules. How many moles of carbon dioxide are in my equation? 2, right? So I need to multiply by 2 moles of CO2 molecules. So in my equation, how many moles of CO double bonds do I have? 4. Any questions? Yes?
Can I count all the bonds and I just multiply by 1 mole? Like I see 2 bonds and I just multiply by 2.
Yeah, so you see 2 of these bonds in this molecule, and because there are 2 of the molecules, there's 4 bonds, and we're doing it in moles, so it's 4 moles. I'm spelling this out because I was getting some blank looks, and I was hoping that maybe that would help. I don't know that it helped. I didn't do that yesterday, and we seemed to get along okay, so let's forget I did that. Here we have 4 moles of water molecules in the equation, right? 4 moles. Each of these has 2 bonds. How many moles of OH bonds do we have? 8. Okay, so now we figured out how many moles of each bond are going to be made and broken. Now we have to go back to our table of bond energies and look some stuff up. So there's some hydrogen-carbon bonds, and the bond energy for that is 414. And we had a hydrogen-oxygen single bond, and that was 464. And we had a carbon-oxygen single bond, and that one was 360. We have a carbon-oxygen double bond, but that's in CO2, so we're going to use the 799. I think that was all of them. And those units are kilojoules per mole. So we're breaking 6 moles of carbon-hydrogen bonds. So the bond energy for that is 414 kilojoules per mole of bonds. So when I multiply this, the moles cancel out, and I get an amount of energy in joules. 6 times 414, 2484. I have 2 moles of carbon-oxygen single bonds. So I find the bond energy for that is 360 kilojoules per mole. So that's what, 720 kilojoules? I've got OH bonds being broken, 2 moles of those. The OH single bond is 464 kilojoules per mole. $928. And, oh, that's what I was missing. I forgot the oxygen-oxygen double bond. So let's go back. Oxygen-oxygen double bond, 498. $498 kilojoules per mole of oxygen-oxygen double bonds that are being broken. We're breaking 3 moles. So 3 times 498. 1494. Any questions? So we've calculated the amount of energy needed to break each of the types of bonds, and so we're going to add these up to find out the total amount of energy needed to break all of the bonds. So 2484 plus 720 plus 928 plus 1494. 5626 kilojoules. We have to put that much energy in to break all the bonds. Then as we form these bonds, energy is going to be released. So when we form a carbon-oxygen double bond, that's releasing energy, so that's negative. That's the negative of the bond energy. So 4 moles of carbon-oxygen double bonds in CO2, 799 kilojoules per mole. Negative. So 4 times negative 799, negative 3196. That many kilojoules of energy being released. The hydrogen-oxygen single bond, it took 464 kilojoules to break it, and it releases 464 kilojoules per mole when you make it. Now we're making 8 moles of that. So 464 times 8. So it's going to get us negative 3712 kilojoules. So we'll add those together. $69.08. That's negative. So we have to put in 5626 and we get out 6908. So the energy change is adding those together. So we've got the 50.
Where's that difference of energy, Joe?
Pardon me?
Where's that difference of energy at?
Well, we're breaking bonds, and that's requiring energy, and we're making bonds, and that's releasing energy.
So how is it releasing more energy on that side than putting in?
Well, how is it releasing more energy than we put in? That's a good question. The thing about this is we're looking at changes in energy. We're not looking at absolutes. So there's not an absolute zero that we're looking at. It's like sea level. So it would be, well, we went up this far and then we went down further. Well, how do you go lower than you were before? Well, I'm just underwater now. So it's just lower than it was before. So we've got that number, and we're going to add what we get out. I'm getting minus 1282. Check my math, please. Thank you. So that's the enthalpy change for this reaction as written. This is where it's a little tricky. What did they ask? What units do we want? Kilojoules per mole. Per mole of what? Well, it's the combustion of methanol. So we're probably looking at kilojoules per mole of methanol. This is 1282 kilojoules for 2 moles of methanol, right? So divide this by 2 moles of methanol. So negative 641 kilojoules per mole. That's the answer that's being requested.
How do they determine all these values?
That's an excellent question. how do they determine all of these? It's happened through a lot of experiments. And the tricky thing is it's difficult to measure just a single thing happening. And so they measured the things that they could, and then they used that information to help them figure out the measurements for other things. A lot of tedious work. No, it's not an educated guess. It's a little bit like, these Hess's law problems we've been looking at. It's like, well, if I know this step and that step, and I know the overall thing, which can be measured relatively easily, then I could figure out what that missing part is. And do that over and over and over again, different people doing it in different labs, finding it different ways, averaging them and all. And that's where we get all that information. Any questions?
How does this relate to like ionization energy? Is there any correlation between the two?
There's not a direct relationship between ionization energy and a problem like this, because here we have no ions being formed. So this is the enthalpy. Well, why did I write it down there? Because I couldn't see. I was zoomed in too far. Hang on. That belongs up there. Delta H for the reaction as written is minus 1282 kilojoules. That tells me that when I burn 2 moles of methanol, this much energy will be released. Ionization energy is taking an atom and pulling an electron off and making a positive ion. So that's different. Any other questions? Bond lengths. We talk about average bond length. We're looking at the average length of a bond between those 2 particular atoms in a large number of compounds, because again, it's going to vary somewhat from compound to compound. We can look at carbon-carbon bonds, triple, double, and single, and we see that an average length for a carbon-carbon triple bond is 120 picometers. A double bond on average is longer, and single bonds are longer still. And the bond length has an inverse correlation with the bond strength. So a strong bond is a short bond, and a long bond would be weaker. If you think about like maybe a stick, if a stick's very long, it's going to be easy to break. If it's very short and the same diameter, it's going to be really hard to break, right? So longer bonds are generally weaker. Here's a table showing average bond lengths. I can't recall ever actually doing anything with these bond lengths, but there they are. You've seen them.